All right, we are now moving on to section 2, and in this chapter, or in this section of the chapter, we are going to really focus on the 4 states of matter. You encounter these 4 states of matter each and every day. Solids, the desk that you are currently sitting on, the pencil or pen you are holding. Liquids, the water that you drink throughout the day. Gas, the air that you breathe in and out. And then plasma. That's the big fiery ball in the sky. Our sun and the other stars are in the plasma state. So first, let's take a look at this solid state. And as we go through these states of matter, I don't want you to think of what is a solid. In other words, the desk is a solid. We are going to be looking at what's going on inside of it that classifies something as a solid, a liquid, a gas, or a plasma. So in the solid state, these particles that make it up, the atoms, are tightly packed together. Okay, we talked last week about all these molecules that are vibrating in place. In a solid, the attraction between each and every one of those particles is so strong that they have a fixed volume and a fixed shape. Okay, that pencil, I can't just come back later and that pencil be, flat as a pancake. It's going to keep that volume and that shape. Okay, this picture is representing how those molecules are tightly held together. I like to think of it as you're sitting in your desk. I could put some bunch of duct tape and tape you to your seat, and you can still wiggle a little bit, but you're really bound to that desk. You are held tightly in place. Second state of matter is the liquid state. Okay, here those attractive forces, those bonds holding the molecules together, okay, are weaker than in the solid state. Because those attractive forces are weaker, liquids, particles, are allowed to slide past each other, which allows them to change shape. And they're going to take the shape of their container. Imagine if I had a gallon of milk. Okay, that milk is in the liquid state and it's holding the shape of the container. If I pour that milk into a glass, it's going to change its shape and take the container of the glass. However, the particles there still cling together. Okay, so they still have a definite volume. 1,000 milliliters of water in a bottle is going to still be 1,000 milliliters of water if I pour it into a pan. Okay, it keeps that same volume, but the shape changes. Okay, I like to think of this as if I loosely tied you to your desk with a bungee cord. Okay, you're going to be able to move around a lot more. Okay, you're going to be able to slide past your desk and go under it, but you're still bound to that desk. You're still attracted to it. The gas state. Here, the particles are much farther apart. They are spread out. Because those particles are so spread out, the forces between them are so weak that they're no longer clung together. They're not stuck to each other. Because of this, gases don't have a definite volume and they don't have a definite shape. They're going to take the shape, whatever their container, but again, they can spread out even more and change their volume. Okay, my analogy here for you guys is you guys are sitting in your desk, there's nothing holding you there. You can move around the classroom as you please. That volume is going to change because when you were tight in this little area, now you can move about the classroom, and that volume, that area that you are taking up has become much greater. Last state of matter is the plasma state. And this is going to be very similar to gases. However, there are some differences, and those differences are what make plasma the most common state of matter in the universe. Okay, plasma is particles that have positive and negative charges. Okay, you can see here in the picture, some of these particles have positive charges, some particles have negative. Other than that, they act very similar to gases. They don't have a definite shape or they don't have a definite volume. The difference here between a gas and a plasma is the charged state. So let's get into now how things change states. Okay, changes in the thermal energy of a matter cause it to change from one state to the other. Remember, when you change the thermal energy, one of the things that you can do to it is heat it up or cool it down. And I think if we talk about ice, water, and water vapor, you can very quickly see how these different states have different temperatures. If I take ice, which we will do in lab on Thursday, and I add thermal energy to it, it's going to go from ice to liquid water. And then if I take that liquid water and I continue to add thermal energy to it, it's going to go from liquid water to gaseous water vapor. And it's going to go through a variety of state changes. The image that you see on your screen right now is very important. Make sure you get this down because you need to know these terms. From a solid to a liquid, melting, liquid to a solid, freezing. Liquid to a gas, vaporization, and then gas to a liquid, condensation. Those are probably the big four that you already know about. Okay, on your pre-reading from yesterday, you saw the words sublimation and deposition. Okay, and they're not addressed in your book. So what are those? Sublimation is going directly from a solid to a gas. We're not going to go into too much detail of it, but if you've ever seen dry ice, okay, it goes from the solid dry ice right to a gas. And then you can have something go directly from a gas to that solid. That's called deposition. It's depositing, going from gas to a solid. The other two, from gas to plasma, plasma to gas, is ionization and then deionization. It's that process of those molecules becoming a charged ion, either a positively charged ion or a negatively charged ion. And then going from plasma to gas, it's losing that charge. So let's take a little bit of a look closer at what goes on during melting. Okay, so what causes that ice cube to move from a solid to liquid water? Well, the difference has to do with temperature. But what is that temperature really doing? Remember, I talked to you guys, we're going to be talking about what's going on with the particles. So as the particles gain energy, okay, they're moving faster. Okay, if you have ever given sugar to a toddler, you know what I'm talking about. That sugar gives them energy and they start moving faster and faster and faster. When they're moving so fast, okay, they're slipped out of their solid state. Remember that tight bond, okay, that kept them locked in place. They're able to slip out of that and into the bond attraction that creates that liquid. Okay. Water and ice both exist at 0 degrees Celsius. What's going on as it goes from ice at -5 degrees Celsius to ice at 0 degrees Celsius? It's gaining thermal energy, but it's still a solid. Then you get from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. And there's extra energy that has to go in to change those bonds, but it doesn't change the temperature. And then after that ice has changed from solid to liquid water at 0 degrees Celsius, now it'll start to increase its temperature again. So there's this thermal energy that's required to change it from solid ice at 0 to liquid water at 0. And that's known as the heat of fusion. And tomorrow when you go through lab, you should be able to see this straight line on your graph as the probeware is collecting that data. That's the heat of fusion. That's this extra energy that goes in, and it doesn't raise the temperature, but that energy is going into changing those attractive forces. Freezing works much the same way. We are just doing the reverse. It's going from liquid water at 0 degrees to solid at 0 degrees, and we're taking energy out, and as you take that energy out, those bonds, attractive forces, strengthen again, and they become attached. Again, as you decrease that average kinetic energy, those bonds move slower. Okay, and they slip back into that ordered arrangement that a solid is known for. On to vaporization. Remember, this is from a liquid to a gas. If you think of what happened with ice from solid to liquid water, it's going to be very similar here from liquid water to gaseous vapor. So as the temperature of the liquid increases, the particles in that liquid move faster. That temperature becomes higher and higher, and eventually the forces between the particles become so weak that they can't hold each other together anymore. So those attractive forces get broken and they're no longer held together. Vaporization can happen two different ways. The first one is evaporation. If you've ever had a bowl of water and you come back 3 or 4 days later, you know how that water is less. Look at the tortoise's water sometime. Okay, I filled it up yesterday all the way up. If you go look at it right now, you're going to see that there is water missing. That water has evaporated. Okay, in evaporation actually causes the temperature of the liquid to decrease because those top surface molecules, for the most part, it can happen within the liquid, but those are the warmest molecules, and those are the ones that are escaping from that liquid bowl of water. The other way to vaporize a liquid to a gas is to boil it. Okay? And boiling occurs throughout the entire liquid. Okay, when you see those bubbles, it's happening throughout the entire liquid. But what really is boiling? Boiling point of the liquid is the temperature at which the pressure inside the liquid is equal to the surface pressure on the liquid. At sea level, we know boiling point as 100 degrees Celsius. Okay, if I heat a glass beaker of water, okay, at sea level, you're going to see that boiling happen at about 100 degrees Celsius. As I change pressure outside the liquid, that's going to change the boiling point. If I go up into the mountains, okay, air pressure is lessened. So it takes less temperature for that boiling point to be reached. So in Denver, Colorado, okay, Mile High City, up 5,280 feet approximately, the boiling point is going to be lessened. If I go on a submarine and I go underneath the ocean, the pressure is greater. So what's going to happen to the boiling point of a liquid there? It's going to be higher. Now, this creates a big difference when it comes to cooking time. If you've ever pulled out a box, whether it's cupcakes, brownies, dehydrated potatoes, like scalloped potatoes and stuff, and you've ever looked at the back of the box, there's two different types of cooking directions on there. There's the one that you've always read, but then if you look, there's going to be at higher altitudes because water boils at a lower temperature. So imagine a pasta. You're cooking pasta in a pot, and you know that you have to cook that pasta for 10 minutes once the water's boiling. Well, that's at 100 degrees Celsius. So what happens if the boiling point of the water is at 96 degrees Celsius? Is your pasta going to get cooked? Or is it going to get overcooked? Okay, it's going to be undercooked. It's not going to have enough time. It didn't get hot enough. The same thing happens with baked goods as well. Okay, you have to adjust your cooking times. Okay, just like at 0 degrees Celsius from solid to liquid, we had that heat of fusion. Here we have the heat of vaporization. And there's going to be this extra energy that's required for water at sea level to go from 100 degrees Celsius liquid water to 100 degrees Celsius water vapor. And that's this heat of vaporization. Again, tomorrow, when you are doing lab and you're going to take it all the way to boiling point, you should see a straight line right around 100 degrees Celsius, and that's going to be that heat of vaporization. Condensation is the reverse process. Okay, heat of vaporization, but now we are reorganizing those molecules together. We're taking out thermal energy, which causes things to go from a gas to a liquid. Your biggest example here of condensation on a hot summer day, if you've ever taken a glass of ice water outside and you set it on the table, you come back 5 minutes later and you see all the water outside on the outside of the glass. It's not that that water has passed through the glass, it's that the water vapor in the air surrounding the glass has lost thermal energy. Okay, it's given its thermal energy to the cup and has decreased its temperature enough for going from water vapor to liquid. Now we need to talk about one last topic when it comes to these state changes. Within each state of matter, there's something called thermal expansion. Okay, if you've ever heard about roads buckling in the summer, okay, the roads heat up and they essentially pop, they explode. Okay, if you've ever looked at a bridge, if you've ever walked over a bridge, you're going to notice these little gaps. Okay, why are those gaps there? Okay, those gaps are called expansion joints. They allow the material to expand. But why do we need these expansion joints? It provides a space for materials on hot summer days so that they don't become warped or cracked. If you've looked on a sidewalk, you've noticed those score lines. Those score lines are just that. They're an expansion joint. So when the hot summer day comes, that solid has room to expand. So thermal expansion happens in all phases of matter. Okay, the kinetic energy explains why this happens. When the temperature increases, the particles move faster. Okay, and as they move faster, they need more space. Those attractive forces become weaker. It doesn't just magically really happen at 0 degrees Celsius. Those attractive forces are constantly becoming weaker. If I move faster and faster, I want to get farther and farther away from other people. So as I become warmer and warmer, as that solid becomes warmer and warmer, the size of the object increases. If any of you guys have hardwood floors in your house, you have little bits of quarter round around the baseboard. And this allows those floors to expand in the summertime. They get hot, they're going to expand. In the winter, when your house is cooler, those boards are going to contract a little bit. It's really important to remember this because if you ever put in your own hardwood floor, you want to make sure you cut the board right. If I am putting boards in right now when my house is cold and I cut those boards the exact length from wall to wall, okay, come summertime when those boards heat up and they expand, they're going to pop and buckle. Okay. Opposite, if I am cutting boards in the summer and I think, oh, I need this expansion joint, and now comes winter and my house is cooler, I could actually end up seeing those gaps. So there's some science to laying hardwood floors. Okay, when it comes to a liquid, it works much the same way. As the liquid increases its temperature, the kinetic energy, those molecules are moving faster, and as they move faster, they want to expand. However, with a liquid, the particle attractive forces are weaker, so it allows much more of that thermal expansion and thermal contraction if you take that thermal energy out. This is how liquid thermometers work. If I stick a thermometer into my boiling water tomorrow, my water with the temperature increases, the liquid inside that thermometer is going to also increase its temperature. And as it increases its temperature, it's going to expand. And that's how we get that temperature reading on a liquid thermometer. Finally, we get thermal expansion in gases. Guess what? It works the exact same way, only now even more of a difference in expansion. Your example here is a hot air balloon. Okay, as I pull the gas and it heats up the air inside that balloon, that air molecules move faster and faster and they want to expand even more. Eventually, it gets to a point where the air inside the balloon has spread out enough where it becomes less dense than the surrounding air. Okay, and once it becomes less dense, it rises. And we'll talk more about that next time, but less dense things rise, more dense things sink. Now I'm floating up in the air in my hot air balloon. I want to come back down. I simply need to stop heating that air inside the balloon as much so that those molecules contract some. The density of the air inside that balloon becomes greater than the surrounding air, and then it will make its way back to the ground. Okay, that's it for this lesson. If you have any questions, please let us know. But when you are done with the Edpuzzle, you need to make sure you are all set to go for lab tomorrow. We will tomorrow have a brief discussion before we get going on lab safety and how to use the Bunsen burners because it will be your first lab using those. Again, I still have a few of you that have not turned in lab safety contracts. You will not be doing lab tomorrow or Friday if that is not in. If you don't know if that's you or not, you need to check in the gradebook online and you will be able to see that. Thanks. Have a great day.